Thank you for joining in my talk. I am Kumar Maity. I am a grad student at University of Massachusetts Amherst. This is a joint work with Professor Arya Mazumdar and Soumyabrata. In this work, I'm going to be talking about high-dimensional discrete integration over the hypergrid. High-dimensional discrete integration over hypergrid, or this kind of problem, is an important problem in machine learning, physics, and statistics and biology. The problem of discrete integration particularly found in probabilistic or graphical model inference type of problem. In inference, we need to compute something called normalizing constant, or furthermore more normally known as partition function. And computing a partition function is a good example of high-dimensional discrete integration. In a problem of discrete integration setup, we have a very large domain omega, which is actually exponentially large in the number of variables. And there is a non-negative function w, which takes configurations from this domain omega and then maps it to a non-negative real number. Our goal is to compute this summation of the weight of all the configurations in polynomial time. As you can see, the sum is over a exponential size set. So computing it in a polynomial time is kind of intractable. So we are going to provide a constant factor approximation in polynomial time of this discrete integration. Potts model is a graphical model and computing the partition function in the Potts model is an example of this discrete integration type of problem. In this Potts model, we have a graph G and a level space Q, and the partition function expression is given in below. As you can see, the expression inside the sum can be dubbed as a W sigma, and sigma is the configuration, and given the configuration, this can be computed very easily. The problem lies in the summation over the domain of the summation. The summation domain is actually exponentially large in the number of vertices or the number of variables. Now, in our problem setup, we choose omega to be q to the power n. That is, n variable is the number of variable, and q is the number of attributes for each variable. And in this problem, we choose q to be greater than 2. There is a weight function w given to the algorithm, or w can be problem specific, which takes configurations from the domain and then maps it to the non-negative real number. To understand the algorithm better, we are considering the following. There is an inherent, without loss of generality, we can assume there is an ordering based on the weight of the configurations, and they are in a non-decreasing manner. We choose parameter r and t. R is less than equal to q minus 1 over 2. We can think of it as a mental note that r is the biggest number, less than q over 2, and t equal to q by r, which is slightly greater than 2. Now we are going to be focusing on a particular sets of weight, which are of the form sigma t to the power I, and we are going to denote these weights as beta I. So we are going to be focusing on for t I equal to 0, 1 to n dash, where sigma t to the power 0 is sigma 1, which is the highest weight, and then tth highest weight, then t square highest weight, t cube highest weight, and so on until the smallest weight, which is the beta n dash, which is actually w sigma q to the power n. Now the full discrete integration can be think of pictorially in the following manner. As the configurations are discrete in nature and are ordered in non-decreasing manner, this is going to be like a step function, and the area under this step function actually is the total summation. Now we can partition the whole summation in different segments. We are here going to focus on the segments in between beta I and beta I plus 1. And if we sum over these such segments, then we get the actual summation. Also, computing such segment is actually can be exponentially large, and the total set is exponentially large, so it is intractable, but we can upper and lower bound it very easily. We can as you can see, that this particular segment can be upper bounded by the rectangle or by rectangle under the maroon curve, and lower bounded by the rectangle under the black line. And if we sum it over different segments, then we get an upper bound and lower bound of the whole sum. And this upper bound and lower bound is denoted is shown on the right side of the slide. Now, it can be easily shown that the upper and lower bound actually t-square factor away from each other. So if we can compute the lower bound with the beta is given, then we can easily get a t-square factor of the actual sum. And as t is slightly more than 2, so we can get a 4 plus O of 1 approximation. Now the problem remains is to estimate the beta I, which we are going to do in the algorithm following. We are going to generate a matrix A and B uniformly at random in the field FQ. And for I equal to 1 to n dash, we're going to solve this following constant optimization problem. The constant optimization problem solves the particular thing. What it does is it considers those configurations such that A sigma plus B is less than equal to R times 1. 1 is the all one vector. So it is going to generate a random set based on that, and we're going to pick the maximum weight of that particular random set, and that is going to serve as a very good estimate for the beta I. Now, for a better estimation, what we can do is we can run this optimization problem k times and take the median of it, and we get a much better estimation. And this technique is also known as a median tree. After we compute all the value of m0 to mn dash, then we can return this, but we can return an approximation of the sum in the following manner given in the fourth point. We also saw in analytically that the approximation quality where mi is a estimate of beta I, which lies in the set beta I plus 1 and beta I minus 1 with high probability. So it's a very good estimation for beta I. And in the following theorem, we showed that with probability 1 minus delta, where delta is any value greater than 0, we showed a q by r square approximation of the summation problem. Where q by r is actually slightly more than 2, so we get like a 4 plus, almost 4 approximation. One more thing to notice is that how many times we need to call the optimization oracle or solve the optimization problem. That is in log n times. So almost in linear number of calls to the oracle, we can solve this problem. For in conclusion, we can say that for Q-2 or for the binary model, previously Ermon et al. And et al. Separately showed a 16-factor approximation. But from going from binary to QRA model, if we do a naive extension of the previous algorithm, it yields a very bad approximation, generally Q-square approximation. For QRA problem, which is our algorithm, which provides 4 plus O of 1 approximation. Also, in our paper, we developed an unconstrained optimization version of this algorithm model based on the paper of Arya. In our paper, we have done a number of experiments. Here we're going to show one of them, where we generate a random graph G. It is a POTS model, partition approximation experiment. And in the POTS model, these are the parameters given. And we compare with the naive extension of the Arya or the unconstrained version of the optimization problem with our method, which is the unconstrained multi-binary algorithm with R equal to 15. And it is easy to see that the red box, which is our algorithm, has the approximation factor very close to 1 compared to the blue circle, which is the naive extension of the Arya paper. And we saw the approximation factor for different number of configurations. And as you can see, the closer the approximation to the 1 is the better approximation. And this shows that our method is actually much better than naive extension, and also our algorithm actually works. Thank you for joining in my talk. For further details and more theoretical and experimental results, please share our paper. Thank you.